All right, thank you, Zach, for the introduction. Yes, my name is Alexandru Dima. I'm a postdoc at UIUC, and today I'm going to talk about some work that I've been doing in collaboration with Chloe Richards, a first-year grad student at UIUC, and our PI, Professor Helvi Vitek. And the preliminary results that I'm about to show you have been produced with the thanks to the Einstein toolkit infrastructure coupled to Canuda, an open source code that has been developed by Helvi and her collaborators to specifically tackle beyond GR physics around black holes and stuff. So thanks to Masha Kunkova's very nice talk on Monday, I hope I don't really have to spend too many words on motivating why people like us care about exotic models like axi-dilaton gravity. But just to recap in a few words, we can now finally test these crazy ideas, if you want to call them like that, against data, because thanks to the LIGO Virgo Kagra collaboration that has gathered around 90 events, as we heard yesterday, in the first 3 runs, and hundreds more are expected to come starting early next year with the 4th run of observation. And if you think about 3rd generation gravitational wave experiments, even thousands more events will be hopefully observed in the near future. So what can we do with this collection of large collection of data that comes from the strong field regime of gravity? Well, we can test our knowledge about how gravity behaves in that regime. And that's the best place to look after corrections to general relativity. And what kind of corrections we might expect? Well, maybe something like this. This is one of the good, well-motivated models beyond GR, if you look at that from the UV perspective. If you remember Masha's talk, you might have seen some of the elements in the effective action that I'm showing here. I've just drawn them in blue and red. These are 2 scalar fields, a dilaton scalar field and an axion pseudoscalar field theta that couple to so-called quadratic curvature operators, the topological invariant Gauss-Bonnet density and the Pontryagin density in red. The model that we are considering here is a sort of generalization of DCS gravity, and about which Chloe will talk a bit more later, and scalar Gauss-Bonnet gravity, in the sense that this is not a trivial generalization. That is, this model we are considering is not just the 2 fields in parallel, but they actually talk to each other. They have a non-negligible coupling that I drew here in magenta, which might seem weird, but is actually pretty well motivated from the UV perspective. That is, this is actually the effective field theory of gravity that you obtain in the low energy limit of heterotic string theory once you do the whole 4D reduction by dimensional compactification and you forget about the higher order contributions. So in a certain sense, this is the minimal truncation of string theory that you can hopefully see in our with our experiments, or at least constrain the existence of these kind of things. Now, without getting too much carried away with discussing the model, I'll just want to remind you what also already Masha introduced on Monday. What are phenomenologically the main effects of this kind of couplings to quadratic operators in the curvature? Basically, black holes have scalar hair of 2 kinds here, because we have 2 fields: axion hair,
5 minutes,
dilaton hair. How does this affect the phenomenology of black hole? Well, you can have these scalarization effects where black holes naturally develop these additionally conserved charges. You can have a modified spectrum of characteristic frequencies, of course, of the black holes, and so on. However, at the end of the day, what we hope to do, hopefully very soon, is compute to obtain a way for accurate, well, first waveform, then we talk about accurate, but at least obtain waveforms in these models of gravity. So what we are interested more in is really looking at the binary dynamics and gravitational wave output when you have these sort of string corrections. And you might, at leading order, let me just say this thing before showing you the preliminary results. At leading order, one expects to kind of understand what axi-dilaton gravity does around black holes from looking at the individual DCS gravity and scalar-Gauss-Bonnet gravity models. But that next to leading order, what we hope to find is like non-trivial effects to the coupling between the two fields. And let me show you what we are finding. In the context of single black holes, we see that indeed, if you start with a GR rotating black hole, the vacuum solution develops scalar hair around it, both in the dilaton and axion hair. And we kind of trust our results because we see that the hair relaxes to approximated semi-analytical solutions that have been computed in the 90s. First, I think, yeah, 95. However, more interestingly, we see some corrections to that, which was what we expected. Here I'm showing you the dilaton monopole and axion dipole moments. We start with a set of simulations where the initial data is a zero field and the field just grows pretty fast around the black hole, but also simulations where the initial data is given by the semi-analytical approximated solution. And we see that there's a wiggle. The semi-analytical solution, so the actual fields evolve away from the semi-analytical solution and relax to something slightly different. And we expect this kind of effects to be larger, of course, if we just simulate the same thing at larger coupling values. But
2 minutes.
Probably the most interesting thing to conclude is what happens to binaries. So let me see if I can retrieve the video. The nice animation that I have to show you. It's a very short one, I promise. So here we are evolving in the background two equal mass non-rotating black holes, initial separation of 6 amps in the decoupling limit. So there's first approximation, no back reaction of the fields on the metric. That's something very complicated to include. We'll leave that for future work. But you can see that initially, maybe if I can pause the video, the animation right in the beginning. The hair around the two black holes is basically negligible because we start with zero field initial conditions, and the thing just grows very fast already in the first orbit.
1 minute, please conclude.
And I think I'll leave it here. Sure. Can you go ahead and read it? No,
Hi, I'll turn my camera on so that I look. Oh, wait. Can you hear me?
Yes.
Okay, wonderful. Thank you. Yeah, so this is
30
wonderful.
seconds.
Yeah, this is wonderful work. This is super exciting. One question that I had about the action regarding the scalar fields, just to sanity check this for myself. If I set, let's say, alpha DCS to 0, do I then just recover EDGB, or does this additional scalar field coupling like continue to source this capital theta scalar field as well?
Yeah, it's something that I've been wondering myself too. Indeed, you retrieve a massless pseudoscalar. Well, it's not really pseudoscalar field at that point, but yeah, if you set alpha DCS to 0, you have still the coupling. The coupling in the original papers doesn't include the G function there in magenta doesn't include an alpha coupling inside, an alpha coupling cost. So yeah, you retrieve an additional scalar field that is coupled to the dilaton field. And I'm still trying to wrap my head around it, to be honest.
And kind of related to that, in the plots that you were showing with the hair, you showed like spin 0.1, 0.5, 0.9.
Yes.
But the spin 0 case, I think, would also be very interesting because, you know, if you just had DCS, you wouldn't get anything. If you had EDGB, you would get something. And so it would be interesting to see how the spin 0 case is modified from the solution that Helvey et al. Got when they just did the EDGB scalar field.
Yes, so for single black holes, I didn't put it in the plot because it was just overlapping too much with the 0.1 spin. But indeed, what we see is that the axion hair is not there. The coupling doesn't source any axion hair. And you can probably, a posteriori, we figured that out also. That makes sense if you look at the field equations. You can sort of redefine the axion field in such a way to reabsorb the coupling to the dilaton in that equation alone. And about corrections to the dilaton hair, yeah, there are, but are a bit smaller than in the other cases.
Great, thank you so much. And again, this is like super exciting work. Thank you.